I don't care. Hello. Can you hear me? Is it going audio over the speakers? Hello, hello. All right. Hey, thanks for coming for our case study. It's meant to be more sort of open forum. If you got questions or things to contribute, please dive in. What we're doing, what we're presenting on is basically a coordination carried out from Savannah District, who've been involved ERDC. And the idea was to carry out an objective validation or objective process to measure in fluid mud environments. So I'm standing up here kind of lonely right now, but there'll be others up here as well, or at least speaking from the group. So you can either come up here and talk or yell from your seat if you want to. I think this room is ours for 30 minutes, and I think there's nothing after this. So I expect that maybe the conversation will continue, and we'll have some discourse with what works in the real world, what doesn't, what we can do next, and what the implications are of these tests. This, I kind of feel like, is what we're going to present here. I feel like is an industry first. This hasn't been done before, to my knowledge, and I think this could revolutionize or at least change the way we deal with dredging and liquid mud environments. Fluid mud. So first, the problem statement. And I'll just keep looking until
All right, so I'm the chief of hydro at the Savannah District. Since I got here, we've run single beam for dredge surveys and conditional surveys on a monthly, ongoing basis. And there's been this constant large separation between our 200 and our 28 kilohertz. So we asked Norbit and HYPACK to come in and sort of help us characterize, why we are seeing this separation, and if what we're doing is correct in terms of navigation safety. Is our 28 kilohertz system appropriate to sort of determine what navigational bottom is in this harbor? As cargo ships get larger and tolerances get sort of tighter, we need to be absolutely sure that what we are conveying to the public and to industry is safety for navigation. So we're hoping that we can move to better technology and better define what navigable bottom is here, specifically in Savannah.
Cool, thanks. So, to continue with that problem statement a little bit, what the job of the surveyor is describing a relatable navigation surface. Because the areas get mapped, they get validated, QC'd, they end up on a chart, and a ship captain from Singapore is using it to come into port, right? So we have to have a common surface that everybody understands. And what is that surface? The question always was, well, what is the depth? What is the bottom? And that came out so many times growing up in this industry. Everybody's like, well, what is the bottom? It's kind of depends on what your acoustics get you to. Turns out there is a bottom, a defined bottom. And a defined bottom is a density amount of grams of material per liter, or whatever unit you want to use. But in the past, what's currently being utilized, as Miles was mentioning, is this kind of shotgun or cannon approach of using a low frequency system and simply map the area and just blast through whatever you see. And when we talk about that, we also have to talk about the subjectivity of it. Well, what pulse length is being used? As a pulse length, or number of cycles, or pulse duration, or pulse width, sometimes called incorrectly, as you increase that, it increases the uncertainty, that increases the noise. You can just sit there and turn your single beam on and slowly start increasing the pulse length, and you'll see the bottom go like this, and all of a sudden, as you increase, it gets bouncing up and down, right? That's the impact of long pulse length. The other side of it is we can't make a pancake low-frequency transducer and efficiently mount that on a boat. It's going to be huge, right? So we've got these beam angles that are huge, they're massive, and the footprint, the effective footprint, so 55 feet of water, gives you a footprint size of 28 feet. Well, now the question is where's the bottom in there, right? What's reported? Is it going to the center of the beam? Well, the reporting, whatever depth it gets, will be reported at the center of the beam, but maybe the depth is coming from over here. Maybe the depth comes from down here, which is the right depth, right? So that's furthering increasing the uncertainty. And so understanding what is the ideal and common frequency we should use, the impact of the footprint size, the pulse length, and now we're only going to survey one line every 200 feet. So what lies between, right? That puts us in a category zone of confidence of B, which means that we are not mapping the full seabed. So imagine the risk for a ship captain coming into port, doesn't know where the bottom is. And I don't know if the story is true, and I don't want somebody to tell me it's not true, because I use a story all the time to describe the problems with single beam. But I recall some years ago in Norfolk Harbor, an anchor of a ship was lost, and they didn't find it. And then a ship was coming in, hit that anchor, slid that along until it hit a hard object, and then tore a couple 100-foot-long gash on the bottom of the ship, and it was taking on water and basically blocked Norfolk Harbor. Yeah, I thought it was true. That's good. So when you're running a survey line every 200 feet, you're going to have that issue, right? You're not getting the full bottom. There's also discussions of, well, what are the volumes going to be? What's the volume calculation? Typically, you're using average end area, right? Okay, well, that's one way to calculate volumes. But what's the impact of that? What's the reliability of that when you're only getting one every 200 feet? And then what if there's mounds? I also heard another story, and I'm going to keep on this. Don't tell me if it's not true. Another story of basically a dredge company just dredging along the 200-foot cross-section line, knowing that that's what the Corps was going to map and validate the survey with. So you had all these high bumps. I know it's true. Okay, good. So before we get into this a little bit more, fluid mud. Some common words we use, and this is just thrown up here randomly. First of all, rheology is basically the study and characterization of fluid mud, hence the name of the instrument used to measure called a rheotune or a densitune. I think they're different manufacturers. And that actually measures the navigable bottom. The navigable bottom, according to some research that's been carried out, is said to be something in the order of 1,200 grams per liter. And then people have their own, everybody says it in their own units, to 1.2 tons per cubic meter. That sounds more robust. 1.2 kilograms per liter, so it's metric system, so move your decimal places where you want. And then we talk about material density, viscosity, the layered media, the ludocline. That's a cool word to bring up at a party. So the ludocline is effectively where your 200 kilohertz starts reflecting off of. And sediment's a funny thing, as I'm learning. I'm not a geologist, but it's cool because typically at about the 200 kilohertz levels where you start having the consolidation that starts. It actually is a bit of a layer. If you look at the water column in a sonar system, you'll see nothing until you hit that ludocline. And now you see that increasing density as you go down through it. So generally, the higher frequency hits that ludocline. And the ludocline is is not the navigable bottom. Ships can travel right through it. And then, if you've got a lot of suspended sediments further down. CATSOC is Category Zone of Confidence. That's one of the requirements for navigation charts. Those are those funny little asterisks you see that you have to remove in HYPACK, right? Every time you open up HYPACK, you got to remove those, quality of information, visual quality of information. Okay, so this came from the Corps of Engineers manual, engineering manual for navigation, for dredging and navigation or something like that. I love this. This is a great image. So what we're seeing here, it's created by a software called Silas. And where's my cursor? Cursor? Well, whatever. You see a red line. So the red line is what's been collected in Gulfport Ship Channel. It was 2011, I think it was. And that's a 24 kilohertz single beam. And then the 200 kilohertz is the lutocline, right? And then you can see there's quite a bit of suspended sediment there in that environment. Turns out that the 1,200 grams per liter level is an orange line, so it's well above it. Is that shocking anybody? Okay, fine. Shocks me, because, what are we doing? We're running out there with low frequency systems. We're blasting with these cannons, pushing down through the water, actually making it deeper with every ping, I think. But we're pinging through the water here at 24 kilohertz with these large footprints, and we're well below what's needed. Okay, it's safe. That's a good thing. But what implications does that have, right? In terms of, are we over dredging? Are we under-reporting the safety? Could bigger ships come through? There's a bunch of other questions, I guess, that comes up. But it's an interesting thing. So basically, go back to that density, and you take these probes, which we've done here as well. You'll drop these probes into the liquid mud, and somebody that's smarter than me can describe how it works. Some little vibrating thing happens, and a tuning fork something or other, and somehow it figures out the density. And it's not an easy. It sounds like an easy sensor to drop and figure out, but then you're dropping it down. It's got a pressure sensor on it, and it's got this really weird reel system to validate the pressure sensor, which seems weird to me because we're dropping sound speed profiles all the time with pressure sensors. We don't have to calibrate them; they just work. So a lot of weird things going on with that. But it's come to be known as kind of the common methodology for determining that navigable surface. That's when the density reaches a point at which the shear stress of a ship passing through it will start having some impacts on its navigation, its ability to maneuver. So turning, it'll slow it down. Imagine a ship is turning and all of a sudden it starts grabbing something with a higher shear stress. That might just cause the ass end to kick out, and now you've just lost control of the vessel. What was that ship, the Ever or something? Evergreen? Yeah. So I don't know what happened there. I think maybe they were just drunk, but something could have happened. Sorry?
I didn't think anybody knew what happened with that ship.
Oh.
I never did hear anything.
No, I haven't heard anything either. I think it was this. Yeah. So carrying on some of the background topic here. I mean, so category zone of confidence is where we need to go. This is what NOAA's been pushing. I did a technical talk about this with the Hydro Society in Houston late last year at some point, and it was picked up almost immediately by NOAA. And next thing you know, there's a large discussion with NOAA on this, and they're really keen to try and figure out how can we get to the navigable bottom. And their goal is to have category zone of confidence 1 or A1 or A2. The numbers are small there, but the depth accuracy values are actually fairly large. It's a 10-meter water depth with a plus or minus 0.6 meters, right? So 60 centimeters is probably about that large, right? So 1.2 meters that's your plus or minus accuracy envelope. And but they want full seafloor search as well, so fully mapped. And what we're dealing with, and this is a learning curve for me, all of it's been a learning curve. I'm still learning right now as I'm standing up in front of you. But if we look at the graph on the right-hand side, we have a kind of a schematic of showing how, you know, the ship is coming into port, it has its draft. I added the yellow part because what it didn't show was dynamic draft. As pitch increases, it might squat and actually have a larger draft value. And what they're looking for is UKC, the underkeel clearance. And they're looking to make sure that they have enough of a buffer zone before they get to the dangerous navigable bottom surface. But the curve on the right is interesting because it shows, in a general sense, how the suspended sediments will, the density of suspended sediments will accelerate pretty quickly the deeper you go, as a suspended sediment is consolidating. And that's interesting. Keep that in mind because as we go through some of the results of our tests, we're going to see that working to our benefit. So the way the sediments are going, they're trickling down. At one point, suddenly there's a threshold, and then they start settling, right? So that's that lutocline area. And as we go further down through that surface, that density increases, and it increases very rapidly at some point. So that's actually good news for us. So where we are right now in our development, I'm wearing a shirt here that says Norbit. So where we are in our development part of this is that, you know, we've had the origins of it. We've figured out that there was a necessity to find a solution. We worked with a few different industry folks on the initial proof of concept, and we're in the field verification phase. After the test we've carried out this week, we're going to start refining it and coming up with and validating that solution to finalize it and then release it into the wild. The previous experience that we had was working with the Corps of Engineers, New Orleans, and they were keen to try and find a solution in their shipping channels. So where we went to the Calcasieu area, river or waterway or something, whatever. So we went to the Calcasieu. We took the I-87, we mounted on the side of their boat using a portus pole. Just clamped it on C-clamps, and we went out there. And it was a lot was going on. We had about 3 days, and we immediately saw some results we didn't quite expect. We immediately saw 2 layers, 2 horizons in the water column. And, well, we didn't know what those were, but it looked promising. And we mapped, and then we did some single beam, and we're driving back along I-10 somewhere, and Cody was processing the data in the car. And as we got maybe about 30 miles outside of New Orleans, probably at like 8 o'clock at night or something like that, he has a plot that you see on the bottom right on his laptop. We took a picture of that just with a phone, sent it to Drew Oakman of the New Orleans district, and he had somebody hand the phone over to him, and he was driving, he looked at it, and then he said, okay, put that away. Blinker goes on, pulled over the side of the car, took a good look at it, and he called me, he said, Mike, I had to pull over the side, I saw this, and I had to yell out a whoop. That was his way of saying he was very excited. What you're seeing there it's very interesting. It looks probably pretty normal for what you're expecting from bathymetry. It's a cutter head sweep sort of motion that you see on the substrate, and you see spud holes. And that was through, what was it, 6-7 feet, Cody, 6-7 feet of suspended sediment. I'm not sure if that's ever been really seen before, right? And what's a spud? Is it 32, or what's the diameter of a spud? Sorry, 36? Okay, so we're easily picking up a 3-foot feature in fluid mud environments. And the consistency, the density of that was anywhere from what was called to me to be like something like eggnog to toothpaste. On the left-hand side, after we got back in, the Corps of Engineers processed the single beam data, and now we compare that against the multi-beam. On the green data, you see the single beam at 24 kilohertz, and then we see our red multi-beam, right? So generally agreeing to within about 0.2 feet. So they just ran their stuff, and we ran our stuff, and that was it. It was a best attempt, but we didn't validate it. It wasn't truly objective unless you grab all the data and go back and and verify it. Are the offsets correct? Was the sound speed applied correctly? And so forth. So that's kind of where we left off. We carried on to do a few more tests. Bill, did you want to talk about that one?
Yeah, I can do that.
Yeah.
Sure.
I just don't want to give any information away I'm not supposed to.
So this test predates my time at Norbit. From my past, I worked with ST Hudson and GBA. So Mike approached us and we wanted to do some testing. And most importantly, we wanted to make sure the testing he had before in proof of concept wasn't regionally specific. Anything works in a vacuum. So this test was the first proof of concept in a different area with different bottom type, a different geographical location, and similar problems anywhere in the southeast Gulf Coast. Fluid mud environments are always plaguing it. So we had a small vessel, vessel of opportunity, clamped on the portus pole, and we can go head to head against existing methods and then scalable, large swath, large coverage methods. And we believe we got the same results. These findings were presented at the Hydrographic Society in Houston as we think we found a solution for this spot, that the numbers are starting to line up. We're starting to trend in the right direction. So these, based on validations, we believed we had a system capable of doing what we needed to do. Then we had to take it a step further and validate it, go against different frequencies, different single beams, 36s, 24s, validate it. So if we have 2/10, is that a real 2/10 or is that a 2/10 in a bias of a survey setup? So we're really constraining factors in this next testing series that I'll let Mike talk about.
So the current methods, as I mentioned, Savannah District contacted us and said, look, we saw your results that you had from the Calcasieu with New Orleans District. We'd like to test more. We have some issues here, and we're not able to map through fluid mud with anything but single beam. And does it work? And then Savannah District coordinated and contact engineering research, ERDIC in Vicksburg. And then ERDIC came with their crew. But the current methods that Savannah District is using, I think most districts are using in these types of conditions, is an echo sounder running at low frequency, a high and a low. A high frequency to pick up the upper consolidation area, the ludocline, and one to pick up the the punch through to the bottom of the liquid mud. And they're running with RTK and they're plate checking, bar checking, and validating all this, and the data quality is good from the single beam perspective. But this is an area that Miles pulled for me. And this is the same area. So this one here, that one, is a survey that was carried out in January last year, right? That's right. That's an after dredge survey. And look how clean it is, right, from a single beam. Nice flat bottom. The suspended sediment layer is above it, which is generally flat because it's, I don't know why, whatever. So, but the dredge area is nice and clean and flat. But look how quickly it's silted back in again. And the second survey was done in December. So that's 11 plus months change. So it's heavy sediment flow, heavy buildup. It's a very quick buildup there. So the teamed approach is ERDIC came with 2 boats from Vicksburg and a full team of these experts. They came with RioTune. That's that system that measures the density in the suspended sediment. That's the only thing that really matters in this whole comparison test, right? Because that's what's going to tell us where the 1,200 grams per liter is. They came with a Odom CV300 that's running both 200 and 24 kilohertz. They also came with a ball valve sampler. So at discrete depths along different cross sections, they collected the sample, bottled it, and it's being sent back to their lab where they're going to analyze it. They also brought another vessel that had an RT Sonic 2026 and also had an EdgeTech sub-bottom profiler on it. I don't, which profiler was that? Do you recall? There's 3400 HYPACK. Savannah District used their survey vessel Maze. That's the yellow boat, or sorry, the white boat that you see on the bottom. And on that, we mobilized the I-87 on a portus pole, as you can see in transit mode there. And also, we employed our layered media detection algorithms, which is kind of an R&D effort. So it's not out of the box, push button operable yet. They also ran their SV Gannett, whatever, and that was running a Knudsen mini sounder, 228 kilohertz. So we're still waiting for the data for ERDC. All of the data we have right now is analyzing and comparing against our multibeam, the ID7 versus the Gannett's 228 kilohertz. And let me just also state, all of this testing started on Tuesday, January 2nd, and it wrapped up Monday, just before this conference. And we got the results Monday at about 10 o'clock, and it was a cause for celebration, I think. So what our test was, we wanted to make this as objective as possible. And to make it objective, we have to prove every sensor that we're utilizing. And we created a control site. And the control site was well downstream in an area that's very sandy. It's a sandy bottom area. And so we call that the QC sandy control, there at the bottom right. So that was surveyed in the beginning of the trial. So that was on the 3rd, I guess, on Wednesday the 3rd. And then was surveyed again on Sunday. So both times. Why both times? Because it's a river and there's sand waves and it's a moving bottom. So we wanted to try and track and see what kind of changes that happened during those 4 or 5 days. Then we went up to an area well upstream, which is a fairly challenging area called King Island Channel, and the upper part of the King Island Turning Basin. Then there's Marsh Island Channel. And that King Island Turning Basin, I mean, you guys have poked your heads outside, you've seen these massive skyscrapers falling on their sides and trucking up the river, right? These ships are huge. I mean, it's awesome, right? And when they go up there, quite often, they're gonna go up there and they're going to turn around, right? And that just churns everything up. It turns into a liquid mud soup. It's crazy. So just imagine as you're seeing those ships coming up there, they have to turn around somewhere, and that's what these turning basins are for. So they have to be dredged well. I mean, that's where they really need their ability to maneuver. And we utilize the Winghead I-87 with layered media detection. And what that system is, it's a curved receiver array. Has an agile penetrator. It's going to go anywhere from about 60 to 450 kilohertz. It's a frequency modulated system. It's anywhere from up to 4,096 beams per ping. It's 2 degrees by 2 degrees at 100 kilohertz, and half degree by half degree at 400 kilohertz. Has multi-detect, multi-swath, all this other stuff. So it's a big system. It's heavy. It's 29 inches long. The heaviness is in that transmitter. It's absolutely full of electronics, because it's employing beam steering in the transmit sector. So in order to get subludocline detections, what we need is low frequency. Only low frequency will penetrate, right? Long wavelength. If I lower my voice like this, the room will probably hear me, right? So because my lower frequency, the lower, longer wavelengths are gonna penetrate through the walls. So we need low frequency, but low frequency isn't enough. We also need FM. We need to push that energy through the water column and not lose the resolution, because we need to see all the discrete different layers that we have in the strata. So we need the ability to have very long pulse lengths to drive lots of energy in, but not lose the resolution. Remember, as pulse length goes up, resolution gets worse. So we need the combination of those three. The practical desires are portability. Can 1 or 2 people easily mount the system and operate it? Can you put it on small boats like we did on the Maze or the Maze? Is it easy to use? Well, right now it's not easy to use. We need Cody, right? And only right now Cody and Pavel that can operate the system. It has to be objective penetrating detection, so repeatable, right? And basically also employed as a conventional sonar system. So can you use it for this, and then use it to go do a full high-resolution structure scan, making use of those half-degree by half-degree beams. So we mounted the system on the maze, and you can see it there. There's a couple close-ups here on the left, on the right-hand side. It's a heavy kit. I mean, the whole case alone with that ridiculous, stupid stainless steel plate there weighs 120 pounds. We're going to ditch that plate and make it a carbon fiber and get down below 100 pounds for easier shipping. But it's a bigger system, right? And then we took the system and we did our objectivity validation. Providing the means of having a system that is validated, and then any surveyor will look at it and say, yeah, it checks the box. So we did a plate check. And what is a plate check? It's a process like we came up at Seahorse Geomatics a number of years ago to prove the accuracy of the measurements of the system. We basically take a 25-foot level rod, put an RTK rover on top of it, and put a horizontal plate at the bottom of the rod, as you see on the little cartoon over there. And we measure that from the top of the plate to the phase center of that antenna. We call that in, or bring that in as our data collector as a rod height. And we take a nice long shot, like a 90 epoch shot on that. Meanwhile, while we're doing that, we're pinging off of it with a sonar system. And then when we ping off of it, and then we don't be humans, don't pick the number on that plate sounding that you want. Take the data, bring it into Excel, average it out, and pull out the Z value from that. And that's what we're looking for. So when we do that, you can see we're getting down to, or these are feet, right? So we're getting to 1/100th of a foot difference. It's tight. We're using a Portis pole. We're getting rid of all the uncertainties of offset measurements. So this is a pretty standard, typical measurement. Actually, this is better, normally within about a centimeter, so about 2/300ths of a foot. And generally, while we're on the topic, if you really want to do this properly for a survey, right now we're using, I think, the same, oh no, here we go. So we're using the same RTK correction source. If you're going to do a survey, what you'd want to do is you want to use a different correction source to truly validate that you're on the right, that the geodetic calculations are being done correctly. So we would PPK one of them and RTK the other. So RTK the plate and PPK your navigation of your vessel. And when we did that, we're within 1/10 of a foot. So it's pretty tight. We did that for the both sonars. The 2026, we did it for the Norbit IADS. We did it for also the single beam aboard the ERDC vessel. But we did not do that on the Gannet because it's somewhere in the middle of the boat. It's hard to get to. So what we did is we went and validated that over the QC Sandy area. ERDC aboard their larger vessel, again, they had the Odom CV300, 224 kilohertz, R2 Sonic 2026 operating at 90 kilohertz. They took discrete samples using the sample measurement device that they have, ball valve sampler. And then they took the Riotune. Now the Riotune is the one that matters the most because that's going to give us our density. But then the goal is that we're going to be able to validate the Riotune against the actual suspended sediment samples and verify that that's 1,200 grams per liter and that was calculated correctly. We're going to wait those data results. There's a lot of processing, a lot to do, so we'll probably get that, I'm guessing, maybe sometime next week or so. But in the meantime, when we went out with the multibeam, we mapped all of those areas, and we were easily picking up that ludocline. Well, that's obvious. That's the first one we're going to get. But we're also getting that second penetration, that low frequency bottom. Okay, and that's great. So the layered media detection firmware package that Pavel had written gives the ability to map both of those layers at the same ping. So it's a dual frequency real-time bathymetry. The sandy control area, see some sand waves here, some flat areas here. So we focus the Riotune probe test in the flat areas to reduce uncertainty. of whether it's in a sand wave area or if that sand wave had migrated. So we'll wait for that, but we can see, I don't know if you can see it, you can see the green and red there on the bottom in the profile. Very nice correlation between the multi-beam and the single beam. So it's tight. Good. Validation. Going up to the King Island Channel area, this is the area that's just ahead of this large turning basin, the King Island turning basin. We can see that we're actually penetrating between 10 to 12 feet in that area using the system, and able to map directly below it. You can see in the area in the top right corner there, central right corner, you can see there's a bit of a slope up there, and at the very, very top there's a slope. So it goes kind of from a harder substrate and all of a sudden just dumps down where it was dredged, and then and we're getting significant penetration in that area. So that was there, and the King Island Channel. And then going downstream, I'll say that's still in the same area. Now we're going to look at some of the reality of the situation. Was it perfect? Well, I don't know. What is perfect? Is single beam perfect? Right? So now we enter the realm of subjectivity. And I suspect everybody's going to have a different answer to this. When you're editing your single beam data, and that's what the echogram you see on the bottom right in HYPACK, and you see you start getting that separation there on the right-hand side, which one are you going to preserve? Are you going to let it digitize to the top? Go to the bottom? Go in between? Slope it? Or are you going to say, okay, we've got a few spikes going up to the upper detection, get rid of those. Most of the spikes go lower, and then you get further out to the right, and all of a sudden you get a few spikes going down, but most of them are staying at the top, and preserve those. So it gets a little bit subjective on how you're going to process that, all the while remembering that your footprint size is 28 feet wide. On the multibeam side, it was pretty clear where the multibeam wanted to go, and we see some difference there. If you look on the left-hand side, the red is a large width of multibeam data taken out, and then you see the green single beam, and it matches perfectly all along, and all of a sudden you see that separation where the multibeam was now tracking that second layer. It's still multiple feet below the ludocline, but it's tracking a thicker surface suddenly, right? A more dense area. If we go just downstream a little bit, we're getting into the King Island turning basin, and that's where the ships are turning, right? And through that process of turning, I suspect, is also churning up all the suspended sediments all the time. So we went there and mapped. We got beautiful results. It was easy. It was, you can see on the bottom, you can't even see where the red dots are, but they're right inside, right on top of the green. There's not even a difference there. Marsh Island Channel, a little bit further down, a different area again. And here we see again, it's almost perfect. Green and red almost on top of each other. Looks like green's maybe a tenth or two or 3/10 above the red 28 kilohertz detection. Out to the right-hand side there again we see that separation. And that separation is the same as what we saw before up in the King Island Channel. And we can see that when there's a thicker layer, it suddenly wants to track that shoaler thicker layer as opposed to the deeper, thicker layer. I thought I had more on this one, but I guess I don't. But so with this, I mean, I guess there leaves some uncertainty in some of these areas. It's not matching that 28 kilohertz every step of the way, but for most part, it is doing it. And we also have to consider that the time since dredging has been many months. When did the dredging occur for Marsh Island? November. So November was when dredging occurred in Marsh Island. And you can see on the side of the channel there, on the eastern side, you know, it starts consolidating there much quicker than it does in the central area. We found, as I said, some interesting things. On the one hand, the layered media detection at 90 kilohertz center frequency with an FM pulse was effectively matching, almost identically, but it was matching very well the 28 kilohertz single beam. So remember that plot that I showed before where we have that increasing density, that acceleration of density as the suspended sediment starts increasing that density area? What we saw was that when we're at that lower frequency, they both match, but also when we're at that higher frequency, that was matching. So the ludocline was matching with our higher frequency. We ended up using 370 kilohertz so that we wouldn't have a multiple. And that's interesting. So 370 kilohertz was matching the same depth as 200 kilohertz, and 90 kilohertz with LMD was matching the same as 28 kilohertz single beam. So further work, we're going to continue on firmware tweaks. We've got some work ahead of us having learned on this, and the goal is for a seamless system, basically push-button operation where you don't need a Cody sitting on your boat. We want to continue testing in different environments, so there's a lot of excitement about this, and the next test is going to be happening in Europe. We want to do a lot more learning in Mississippi Delta. Corps of Engineers, New Orleans has jumped on this full on, and they've purchased a system. It's getting hull mounted aboard their Tobin this month, I think, and we're going to continue with the testing of that. And the next thing is we want to do is, since the system worked too well, right? Our goal wasn't really just to match 28 kilohertz. Our goal was to get to 1,200 grams per liter. And 1,200 grams per liter, as we saw from the Corps of Engineers navigation manual, is well above the 24 kilohertz surface that they had on that plot, if you recall. So what we want to do now is we want to start increasing the frequency, and we did that on the last day, actually. We drove a couple cross sections that ERDIC recommended that we should run, where they had the most number of samples for the Rio tune and physical samples. And we ran that multiple times, gradually increasing the frequency every 10 kilohertz. And the goal is, hopefully with the results, maybe we can find maybe 135 kilohertz is what we need to focus on for ludocline mapping. Or sorry, for navigation bottom mapping. Yes, sir.
Starting off, the Q&A is starting in the other room. We're a little bit late to that already, but just the other session's already started.
Okay, so wrap up. Or if anybody needs to leave for that. Yeah, thank you.
Thank you.
So this is getting mounted on there, and that's good. And my last takeaway message is this. There is finally a reasonable solution for fluid mud mapping. And there is the ability now to start considering category zone of confidence A1 even. Remember 60 centimeters, I think is what it was, wasn't it? I'm looking at you guys over there. 1 meter cube detection as well. So that's the other thing, drop a 1 meter cube in liquid mud and map that. And validate that. But in terms of density,
And tell me how big the sphere is. Does a 1 meter measured cube look like a 2 meter cube?
yeah, but is that a problem? No, I think as long as we detect it, right? Yeah. So getting to A1, A2 classification is where we need to go. I think what we should do further testing with, having a platform and an environment that has fluid mud, like New Orleans has, is great. It's generally wide, quotes around wide, because it's not wide in the bathymetric sense like we're normally used to. It's restricted, right? There's a lot more noise when you're grazing through that suspended sediment. You know, we have to crank it down. What swath width were we getting? 90 to 100. But I recall that in the upper area, it got like the very, very north end, King Island Channel. Didn't we have to crank it down effectively to about like 80 or 70 or 80? Yeah, so when it gets really thick, you do got to crank down your swath. Yeah. So err on the side of caution on that one. I'd rather everybody run at 70 kilohertz just to be safe. Yeah. Yes, sir. Good.
Define reasonable in dollars.
What is the cost of a ship running aground or losing control?
You are correct.
Thank you. It's less than that. Yeah. Any other questions? All right. Thank you. Just to let you know, we do have the system on the boat. If you want to see it today or you want to see it tomorrow, just come by the Norbit booth and come on board. Thank you.